speak to this nice audience. I'm so sad that I could not be there with you, but I will at the next occasion. So I wanted to show myself, but here the connection is not so safe, so probably I will take off the video. So now you should see my screen. Can you see the slides? Great. Okay, so as anticipated by the title of my talk, sorry, I'll try to take off this 1 second. I think better now. So I will report about some recent results by the experiment I am part of. It's called VIP. And mainly I will focus on what are the two main streams of the experiment, which are tests of fundamental symmetries. These we do by searching for tiny violations of Pauli principle in atomic transitions. And the second big stream is the investigation of dynamical collapse models, and there we look for faint radiation typically predicted by this model, which is called spontaneous radiation. Probably Sandro already spoke and mentioned this. And I have chosen these two items because as ourselves recently realized, they are strongly intertwined, and this relation is mainly due to the relation to the gravitational aspects of quantum mechanics or the reverse. So where we perform the experiments, we set up them in a laboratory near Rome, but we perform them in Gran Sasso lab. This laboratory is very nice. Is several galleries literally built inside the tallest mountain of central Italy, indeed, almost 3,000 meters high. And this means an enormous reduction of cosmic flux, essentially. So this is a very good environment where to perform experiments where you look for extremely low rate of expected signal, obviously. So let me start with the symmetries part of my talk. As you know very well, there are several formulations of the spin statistic theorem, but essentially the main pillars are common to all of them, reformulated in any way, are locality and Poincare symmetry. Now, Greenberg, who is the personality who probably spent most of his life and most of anyone in investigating spin statistics and possible deviations from it, in one of his last talks foresaw, which are still known as to be the possible violations of standard model, which induce also a violation of spin statistics. And today I will concentrate somehow on CPT is quite obvious because the pillars of spin statistics and CPT are the same. I will concentrate on locality, on discrete space, and on non-commutative geometry. So this will be in few slides the main item of this part of the talk. But before going there, I wanted to mention that another class of models, there are essentially two classes of models in this field, which directly imply two different ways to test them. Greenberg himself, together with other collaborators, is the father of QA model, which is the paradigm of this class of local quantum field theories with, I call them static deformations of the algebra. So essentially you see that you have this Q parameter, which interpolates in between -1 and 1, but it's a constant, okay? All these class of models, also other formulation by Rahal, Kampa, Ignatiev, and others, are subject rightly to a super selection which is very simple. So in standard quantum field theory, the Hamiltonian quantum mechanics imaging is totally symmetric in the dynamical variables of all the identical particles of your system, which means that even if you assume that the wave function has a small mixed symmetry component, your Hamiltonian will only connect mixed to mixed symmetry states. I hope that you can see my pointer, I think. So experimentally, what does this mean? That if you take a target isolated, closed, without introducing any new fermion in a system, you will never see any signal of a transition from Pauli allowed to a Pauli violating state. So to test this kind of models, you have to introduce new fermions in the system, as exemplified by this drawing. For example, we do it by pushing a direct current into a conductive target. And these kind of tests are usually called open systems tests. There are several. The other class of models, I will mainly be concentrated on these, come from a recent amazing paradigm that indeed you expect deviations from spin statistics in quantum gravity. The typical example is non-commutative geometry. Just few words. So in quantum mechanics, where the scales are relatively large and the energy is relatively low, the phase space is continuous smooth manifold. But if you go close to the Planck scale, then combining Heisenberg and the expectation of general relativity, you can produce black holes, and this is not true anymore. Moreover, the simple commutation relations between space-time points are also expected no longer to be valid. This is essentially non-commutativity. So in general,
Kristian, your audio is cut off. Oh, no. On Zoom it's working? We stopped hearing you here on the auditorium, Kristian. Just a minute. Try talking again. No, it's not working here. I think he disconnected. Yeah, he disconnected. Yeah.
oh my God, can you hear me?
Now we can. You're back.
Sorry, when you lost me. Oh, this is terrible. I'm at the lab, and these days there are some problems with the connection.
Where is the we are seeing your screen already. You can continue.
Okay.
If you show us the slides, maybe we can tell you where it stopped.
Okay, can you see them?
Yes.
Okay, so I was speaking about non-commutative space-time.
Continue.
Okay. So as I was saying, these formulations have some common denominators, namely that Messier-Greenberg is not obviously valid anymore. And also the phenomenology is extremely interesting because the PP violation probability depends on the transition energy, depends on the energy scale of the new physics emergency, and probably it should also have some not isotropic corrections. So in both cases, open and closed systems, what we look for is a very simple signature. For example, we search for a Pauli violating K alpha transition, namely from the 2p to the 1s state. And imagine that what happens is that since you have a second electron in the fundamental state, then the screening of the nucleus is bigger. So the K alpha, the energy of the transition is shifted downwards. For example, in copper, is shifted of 300 electron volts, and this shift is bigger with the atomic, is growing with the atomic number. So from this drawing, you see what you would expect to measure if you have a Pauli violation. This is the standard line, whose width is your experimental resolution. And then shifted of about 300 electron volt, you would see some signal of violation, okay? So let me start with this open system, so the test of Greenberg, of Q1 and cousin models. So as anticipated, what we do here is to push a direct current, for example, in a copper target, and to look for this signal. The detectors which we use are the better in this energy region, silicon reef detectors, thick a bit less than 500 microns, with an excellent resolution, which we recently pioneered to lower than 119 electron volt at 8 keV, which is the K alpha of copper. And essentially, just to show you, this is our goal here was to improve the previous result pioneered by Ramberg and Snow of at least 4 orders of magnitude. And after 2 years of data taking, we achieved this result, which is actually the strongest bound on this class of models, so respecting this Messier-Greenberg super selection. Now here the perspective following a suggestion by Okun is to continue to test, so to constrain this probability over the periodic table. As you can imagine, as you increase the atomic number, the energy of the transition is higher, so the quantum efficiency of your silicon detector is lowering, and this is the reason why we are producing an avant-garde family of detectors in collaboration with FBK and Polytechnic of Milano. For example, here in the region of silver, we already succeeded to double the quantum efficiency with respect to the standard detectors. So by this, we will cover the region of atomic numbers in between 40 and 50. This is under finalization. The realization of this experiment will be installed next year. And also we started a collaboration with Gator, which is a germanium facility, to explore that region of the atomic table where silicon is not usable, because you cannot go too much farther this limit. So for example, for lead, for gold, for platinum, and these kind of elements. And we already performed a test measurement, which was just accepted. We improved of about 1 order of magnitude the previous measurement in lead. Okay, so let me go to closed systems. So this new paradigm is extremely interesting. Let me exemplify a lot the idea. For example, if you take non-commutativity, as I said, which is common to several quantum gravity scenarios, then you necessarily have a deformation of Lorentz symmetry and also of locality, which means that spin statistics is violated. not anymore constrained by this quantum mechanical result, by this super selection rule. And the PP violation probability explicitly depends on the energy of the transitions that you are measuring and on the energy scale of your model. So non-commutativity means, for example, that you recover a foam-like structure for space-time, which is obviously common to quantum gravity scenarios. For example, it was demonstrated that in string theory, non-commutative geometry is needed for the stability of the theory and to recover the standard model results. And it's also very well studied by Amelino Gamelia, Antonino, again, in loop quantum gravity, where it could emerge at mesoscopic scales. So Theta Poincare is very well studied because it's probably the most promising framework which allows to include some crucial aspects of quantum gravity in the context of quantum field theories. It describes a class of spacetimes which are characterized by, by these canonical commutation relations, where this is an antisymmetric tensor and this is the scale of emergence of non-commutativity. And in brief, what you expect is when the energy is much smaller than lambda, then the PP violation is highly suppressed, and this is the obvious reason why we don't observe it normally. And as I said, very concrete prediction was recently done by Andrea and Antonino, who, depending on what you impose for the electric-like components of the theta tensor, which is related to that Simonu which I showed you before, for example, if they are vanishing or not, you obtain different predictions for the deviation from the standard transition probability. So this delta square is your correction, which depends on the energies of your experiment and on lambda, okay? This is how the delta square is connected to Q of Q-on theory, but as I said, in Q-on you don't have any dependence on the energy. So the experimental strategy is very simple. You put some constraints on the probability to violate statistics, and this you translate immediately into a bound on lambda, depending on what you choose for the theta tensor. So the experiment is based on high purity germanium detectors. This is a schematic representation. Here you see, for example, a crystal of 2 kilograms, which was completely surrounded by some cylindrical sections of extreme radio pure lead. It's Roman lead. Okay, and then some complex shieldings all around. I don't enter in the details, which you can find here if you are interested. The statistical model, the only thing that I wanted to underline is that in this analysis, for the first time accounted for this predicted energy dependence of the PP violation probability. So for example, this green dinosaur here shows you what you expect with arbitrary scale normalization for the whole violating K complex in lead in the case of theta Poincare. So this is model dependent. If you change your non-commutative model in the family, you will expect something different. I will show you. So this is essentially described by this function where the yields of the various transitions are given by your theoretical expectation. And then what you do is you calculate how many counts you expect in your measurement, and you compare with the measurement itself. It's very simple in conception. This is the result, the joint posterior distribution function marginalized over the expected signal, from which you see we got extremely strong bounds. So in the case in which the electric-like components are non-vanishing, the model is excluded up to the Planck scale, far up. And when they are 0, to a bit less than 1/10 of the Planck scale. This improved about 2 orders of magnitude with respect to the previous experiment. Okay, rapidly also, always in collaboration with Antonino, Andrea, we applied an analytic expansion. So we reperformed the analysis by expanding in power series of the ratio of the energy over the energy scale. And this allows, by varying this power key, to look into different classes of equivalence. So for example, for key equal 1, you recover key Poincaré. This is interesting because here, depending on the quantization procedure that you assume you have different predictions. And we can exclude, this was already done, and I think the strongest bound is by the Dama collaboration, the quantization scheme by Arzano and Marciano, while, for example, in the Freidel-Kowalski Gliman-Novak procedure, you don't have Pauli violation. And also interesting that for the first time, we explored the case of triply special relativity, where we put the first upper bound on lambda, lower bound on lambda. This is the analysis, for example, for triply special relativity. I don't enter in the detail, just I wanted to show you, you can recognize how different is the shape of your expected signal with respect to theta Poincaré. So to conclude this part of the talk, I just wanted to give you a very, very preliminary result, which we started to investigate what happens in minimal length models. So again, this is quite common in quantum gravity candidates. And the existence of a minimal length of the order of the Planck scale implies that you have to deform Heisenberg this way through this beta parameter, which sets the scale where you expect the emergence of the minimal length. Again, for example, it was demonstrated that this emerges in string theory. And if you try to construct field theory in this context, this was done. We are collaborating with Bosso, Petruziello, and Illuminati. You again find the deformation of statistics. In this case, for example, the probability looks like this, where this is an atomic transition, m is the mass of the electron, this is the energy of the transition, and this the energy scale where the minimal length emerges. Very preliminary result is again very strong. You see how strongly is constrained the energy scale, probably more familiar for people working in GOOP or in minimal length is beta. And you see that with Pauli violation, you constrain to less than 3.7 in squared Planck energies, which is very strong compared to other observables. In the future, we want to improve on these scales. We will try to get the Planck scale for all the constraints. And also, we are looking into possible anisotropies in theta Poincaré, which could be related to the theta tensor. So a dependence on the angular distribution of the photon emitted, the momentum of the photon with respect to the momentum of the incoming electron. So rapidly, I still have some 10 minutes, I see. I go to the last part of my talk, which is related to tests of collapse models. So I'm sure that Sandro and others nicely introduced, so let me just recap very briefly. Dynamical collapse wants to answer to the measurement problem, essentially, and we know now that if you stochastically and non-linearly modify the Schrödinger dynamics, then you get this continuous collapse by progressively increasing the mass, the complexity of your system. Now, what for me is extremely interesting, and I use here the words of Lajos Diósi from a recent talk, spontaneous universal collapse in massive degrees of freedom, he says, assuming a fundamental gravity-related irreversibility, may have perspectives for quantum cosmology as well. This, I think, is an amazing recent topic. I interpret like this, that if we know that spontaneous decoherence emerges from some space-time indeterminacy, analogously, we have some irreversibility in quantum gravity when we reach the Planck scale, and as Lajos shows, this leads to similar structures for the master equations. And you imagine, no, that this intertwining spin statistics with collapse could provide experimental ways to test these models. Very, very briefly, the Diósi-Penrose is the prototype for gravity-related models. I just use, let's see, the Diósi scheme. So he requires an absolute indeterminacy for the gravitational field. So this is the gravitational Newtonian potential becomes stochastic. The mean corresponds to the Newton potential, and it has a correlation which is given by this expression. This comes from the fact that if you have an uncertainty in local time, then you have the coherence in the energy degrees of freedom. For example, you see this from the evolution of the density matrix. If you calculate the statistical mean of the diagonal terms, they decay exponentially in time. And so time uncertainty, Lajos relates to uncertainty on the local gravitational potential. And he finds this equation. I'm sure that it was shown, is typical, this Lindblad form of the of the master equation, which suppresses the superpositions of local energy. Now, what's interesting is that the damping time, the rate, indeed, is nothing but the self-gravitational energy of the difference between the mass distribution in the two states in superposition. And even if this model would be, in principle, parameter-free, this would diverge for a point-like particle. So you are forced to introduce a cutoff, which is usually known as R0. I will call it correlation length. We also have in CSL a correlation length and so on. So what we look for, we knew, and this was recently impressively demonstrated by Sandro, that an unavoidable side effect of the collapse dynamics is that the quantum state interacts with this stochastic field. So you have Brownian-like motion. So if the particle is charged, it emits radiation. This is called spontaneous radiation. And what we look is this emission from the germanium crystal, for example, which is an active target in this case, and all the materials. This is unavoidable. So everything emits. It's expected to emit. So the strategy experimentally is very simple. You try, we have extremely complicated simulations of all the known background processes in our detector. Then you compare the residual spectrum with the theoretical prediction. And if you don't see any significant signal, you can extract the density functions of the model parameters to constrain them. Now, I will just concentrate on one point. Till now, the experiments were performed at high energies in the gamma rays, where the theoretical expectation, this is for the Diósi-Penrose and this to compare for the CSL, was very simple. You see that the energy dependence is the same, so the shape of this rate of this energy spectrum is common to any collapse mechanism. It's just you have a different yield, which is given by constants of nature and by the parameters of the model. And why this happens is that when the energy is big, the wavelength of the photon that you are observing is intermediate in between the dimension of the nucleus and that of the atomic orbits. This makes that the protons emit coherently, so quadratically, and the electrons linearly, independently. In the gamma rays, we performed a very strong experiment where we bounded, for example, the correlation length of the dp to half an Armstrong. Please remember this number, half an Armstrong. This also, for example, exceeded of 1 order of magnitude the expectation by Penrose in his simplest formulation of the model. Also, we constrained, obviously, the CSL. But what happened? What's going on now? The people is trying to look for signal of spontaneous radiation in the X-rays. For example, Majorana recently, with a higher exposure, set a very strong bound on R0, but they use the same rate which we used in the gamma rays, and this is not correct. In 2 words, what we showed is that if the energy is smaller, then the wavelength of the photon becomes comparable with the dimensions of the atomic orbits. For example, if you take X-rays means keV range, no? So if you take a photon of 15 keV, the wavelength is near 1 Armstrong. And the orbital structure, for example, of germanium, which is used in this experiment, is that the inner mean radius is 0.03 Armstrong and the outer 1.5. So this photon is exactly here in the orbitals. So when this happens, and when also the correlation length is at least bigger than the smallest atomic orbit, something interesting happens. That the electrons start to emit coherently, so also them would like to emit quadratically. But since their charge is opposite to those of the protons, you have some cancellation. So look what happens at the spectrum. The red one is the correct one. The blue is the old expectation, which is just valid. You see that you recover this behavior in the gamma rays. So 2 interesting stuff. First of all, if you compare the emission for different atoms, you have a different shape. This is obvious because you have a dependence on the atomic structure. And imagine how interesting this is experimentally to reduce, for example, the systematic uncertainties. And the other is a conceptual interesting difference. So for the first time, you expect different shape of this radiation for different collapse mechanisms. Here, just for curiosity, this part is the old rate, and this is how you must to generalize it in the X-rays. So this opens really a very interesting new experimental perspective to test established but also new models which are linking gravity and quantum mechanics. As I said, spontaneous radiation and violation of statistics can be intertwined to search for 2 golden channels of the same theories. For example, for minimal length, we are doing this. We are looking what's the spectrum of the spontaneous radiation. And also, we are starting to have a look if possibly there is also an observable spontaneous radiation signature for the post-quantum theory of classical gravity scenario. And with this, I thank you.
Questions?
For a few seconds, I was panicked that I lost the connection again.
Okay, so thanks, Kristian, for the talk. I have a question about the theta Minkowski spacetime on the bounds on the spin statistics theorem. And then, because usually in the case of these non-commutative spacetimes, let's say the energy scale of the correction, of the modification, it needs to take into account the number of elementary particles involved in the probe, let's say. So yes. I would like to know if this is taken into account, and what's the, let's say, so I mean, instead of constraining it comparing to the Planck energy, that should be compared with the number of elementary particles times the Planck energy. So, and if this is the case, I would like to know if what's the order of magnitude of the elementary particles involved in this probe?
Yeah, you are right. You have an amplification factor, which is given by the number of particles that you are testing. The problem is not trivial, and it took a bit to draw the correct model. Obviously, this amplification factor is proportional to the number of atoms which act independently in your observable. But then if you analyze carefully the problem, you realize that not all the electrons of each atomic structure can be involved in the calculation, but just the lower lying electrons of for each transition, those, for example, for the K alpha, you just have to consider the 6 electrons of the 2p level and so on. And this essentially comes from the fact that each subsequent Pauli violating transition scales with the probability which is multiplied by delta square for each transition.
Yeah, I'm asking because in this case, the number of particles, it de-amplifies actually the effect, because the effect gets suppressed by the number of particles, because the new scale would be the number of particles times the energy, let's say the Planck energy or the quantum gravity energy.
But imagine that here your signal is nothing but by counts, for example, in this energy bin. So what's the number of counts that you expect? For each violating transition, you have a count, no? And the number of violating transition is damped by the quantum gravity probability, which is given by the theory. This is a correction to the 1 over the tau of the standard transition, no? And then it scales with the number of particles that are allowed at the first order in this parameter to perform that transition, essentially.
So if I may ask another question.
Yeah.
So you had one very strong bound, like 10 to the 2, I think, times the Planck energy. Yeah, so you'd say that this case is ruled out. How strong can be the conclusions from this bound that has been put?
Yes, definitely. I would say that in the case in which the electric-like components are non-vanishing, this is ruled out. But I'm not a theoretician, but as I well understood the case in which you can unitarize the problem is the other one, so this could come also quite naturally, not?
Yes, and in this case, the theta are constants, right? But in kappa Minkowski spacetime, I think the theta is a function of the spatial coordinate. So are there any prospects to see these cases in which theta is a function of position?
To be honest, the case of kappa Minkowski, we don't plan to explore it in more detail. We already knew that, so here also, as you mentioned, you have an energy dependence. So depending on the target that you use, you can be more or less sensitive. We knew that for the case key equal 1, Dama was more sensitive than us, and we demonstrated it. In any case, in this scenario, this quantization procedure, which I mentioned by Antonino and Arzano, was already ruled out by Dama up to much above the Planck scale. So we don't plan to go further in this context.
Okay, thank you.
You are welcome.
Let's thank our speaker again.